Guys, bear with me. Okay, so I wanted to show you what, this is hopefully going to look like. I'm going to go to student view here. Oh, this is maddening. Because I want you to notice a couple of things. And then Emily and Caden, could one of you let me know, are you seeing my canvas on your screen, hopefully, as I'm presenting to you? Why didn't it go to student view? Okay, so your view on your home page is just going to show this basic information here. You're only going to have access to announcements and assignments. Anything I want you to navigate to, I'm going to give you links for, okay? So I don't need you to deal with modules. I don't need you to deal with pages. I don't need you to deal with anything else. Anything I want you to navigate to, you're going to navigate to just using links that I give you, okay? So that's how I've set my course up. And so you're just going to have access to announcements and assignments as far as this goes. The things that I've given you, in case you have to be, if you have to be quarantined or go online for a while, there's instructions for online streaming here. And the people that are online streaming this class right now, at least Emily and Caden Bird, have already looked at these because they're already here. But these are pretty thoroughly detailed instructions about how to accomplish that. And I'm really hoping that things are going to go a little bit faster in the future here. But I've given you the rules for online streaming, and then I've given you pictures about how to get to all of these things. So it goes into great detail, and hopefully that'll be good enough for you. The other thing is that because we're live streaming these every day, my intent is going to be to have all of this online before. And so there's a page that's going to say a list of available lectures and corresponding class notes. And you'll be able to go to that if you're online. And so today we're going to be talking about friction, and that will take you to that set of class notes. And then that set of class notes will provide you with some information about what's going to happen that day. This is our, we're in our dynamics chapter. For online students, click there to download the participation worksheet. And obviously the video that we're recording isn't going to be available yet until after we record it. So I'm recording right now, and hopefully that's working. Yep, looks to be. And so that link will come up. And then if you want an actual copy of the class notes, and I gave you all a copy of these notes before, but they're all going to be online here. And so everything that we're going to talk about is going to be here. So you in class can either follow me on Canvas, as well as you're going to have to fill out your participation worksheet, and that will be your record of the fact that you participated. You'll turn those in, and I will hand them back to you the next time. But as far as all of the information goes, all the information you need, this is your textbook right here, okay? So And you'll notice that where I've left the blanks, if you hover over it for long enough, it will actually give you the answer for what's there.
Oh, no.
Okay? So you don't have to worry about blanks not being filled in and things like that. But I would keep your participation worksheets just so you can have the solutions to the problems that we're going to do, because the solutions to the problems aren't going to be written out. Okay? So this is the student view. Any questions about, oh, the other thing is occasionally as I get better and better at this, we're going to try and throw a Nearpod in here. So sometimes you'll have to use your Chromebook for Nearpod as well. For right now, it's all I can do to keep up, though, just being able to put the notes online. So, and then there's also a click back to the list of lectures and class notes. Okay, so I am going to stop sharing this particular screen, and then I'm going to start sharing another screen here. So stop presenting. The problem with all of this is that it would be nice if I could just project the Canvas notes that I have that you see online up here and share that with you as I'm messing with it. But I can't write directly onto a browser, so I have to do a little kind of a workaround. So I had to create a PDF of except I don't want the chemistry one. Okay, and so this is a PDF that I can write on. And once again, Emily and Caden, I'm going to ask if you can see this PDF that I'm sharing here. Okay, it says Dynamics, and it's not exactly the same as what's in Canvas, but it's close enough. So if one of you could type, yeah, I can see this Dynamics page, that'd be great. Why did it go away? Is it now? Yes, Caden, that's right. It should come back. There it goes. Okay. So if that's the page that you're seeing there, then we're good. Okay. So it only took me till 1/4 to get to this point where we're actually going to start talking about what we need to talk about today. Okay. And actually, I've already started writing in there. I did that before. So we need to talk about friction today. We're talking about forces, and one of the forces that make it so that life is very confusing when we try to talk about physics is friction, because when we try to push something or pull something, friction is something that sucks energy out of that motion and slows things down. Whereas we've said, according to Newton's first law, an object that we put into motion is going to stay in motion as long as there are no outside forces acting on it. And that's counterintuitive, because we see things slow down and come to a stop. But the outside force that's acting on it, once we stop pushing something, is friction. So it's almost certainly been your experience that when you push or pull an object, you need to apply an increasing force to overcome the force of friction until you seem to break the force due to friction and the object starts moving. A good example would be one of these tables here. I could go up to one of these tables and just start pushing on it, and it's not going anywhere, is it? So I push a little harder, and it's still not going anywhere. And finally, I break that force due to friction, and we have the object start to move. It starts to accelerate. Now, after the object starts moving, what do you notice about how easy it is to keep the object moving compared to the force it took to start the object in motion? And I've seen you already start writing this down. Once the object starts moving, it seems to take less force to keep moving, right? Once I get it going, it seems to take less force. And that's going to be a clue for us to see how the force of friction actually works. And so we're going to call the force of friction acting before the object starts to move the static friction, and we're going to call the force after it starts moving the kinetic friction. And that makes sense. What does the word static mean?
Not moving.
Not moving, okay? It's still. It's in a state of stasis, right? It's static, it's not moving. And kinetic means that it is moving. Okay? So let's look at this graph. Consider the graph above. ACT tests are great places to see graphs, and how to interpret them is a significant thing that the College Board is looking for. And you don't have to know anything about this in order to be able to interpret a graph like this. So the graph above models what happens when force is applied to an object, for example, to a heavy table, both before the table starts moving and then after it stops moving. And let me once again ask, can my online people see what I'm doing? Can my online people see that? And let me like I said, it's going to take me a while. Okay, great. Okay, so basic graph skills. What variables on the, oops, and see, I shouldn't have written that in there. And you guys all wrote that down, didn't you? You should have wondered, hey, Marshall, that's not the right answer. What variable is on the x-axis if I look at this?
Applied force.
Applied force is on the x-axis, right? And then what's on the x-axis, or the y-axis, I mean?
Friction force.
So the friction force. Okay, so when we're graphing, the graph is supposed to help us visualize the relationship between two variables. What happens to one variable when we do something to the other variable? So you can see that if I increase the applied force, the force due to friction is doing what here? When I increase this applied force, what's happening to the force due to friction? At least to start with. If I increase the applied force, what's happening to the force due to friction? I'm pushing on the table. I push with 0 newtons. Then I push with 10 newtons. Then I push with 20 newtons. What's happening to the force of friction on the table? What's the graph show? If I go to 10 newtons, what happens to the friction force? It increases to 10 newtons. If I increase my force to 20 newtons, what happens to the friction force? Goes to 20 newtons. And how do I know that that has to be true? If I come up to this table and I push on it with a force of 10 newtons,
how do I know what's pushing back on me? The friction force is pushing back on me with a force of 10 newtons. It's not what? Okay, it's not moving. That's the phrase that I don't like. It's not doing what? It's not accelerating, is it? Okay? And so I know this has to be true. I increase that force to 30 newtons. And the friction force also has to increase to 30 newtons, right? Otherwise, I would have acceleration of the table. And then finally, I increase that force to enough force where the table, the friction breaks. Okay? Now, normally we place the variable we're changing on the x-axis, and we call that the what variable? The independent variable, right? That's the independent variable because it doesn't depend on anything. We're changing it. And then we call the variable on the y-axis the dependent variable because it depends on what happens to the independent variable. Okay, so we're able to see that the relationship between the friction force and the applied force is that the friction force depends on the applied force. The greater the applied force, the greater the friction force. Otherwise, it would start accelerating, right? Okay, so in this case, the graph tells us something especially important about the force due to friction and its relationship to the applied force. I need to... And you guys online, just holler if you stop being able to see something, okay? In this case, the graph tells us something especially important about the force due to friction and its relationship to the applied force. What do you think this might be? What's that relationship? We just said it already. And I'm going to write down here what I want you to say. Until the object starts moving, the force of friction, the surface exerts on the object increases and balances the applied force. Okay? Until the object starts moving, the force of friction on the surface increases and balances the applied force so that it can accelerate, right? Now, some of you have probably already figured out that you can use your Chromebook to figure out what the answers are before I show them.
Yeah.
Okay? And that's fine. That's good. I just want you to have this information, and I want you to write this down because we're going to start making claims about physical situations and writing explanations as to why our claim is correct. Okay? We need to be able to start writing what we think about this in an intelligent sort of way. Okay, so I've said, all right, I want you to circle the part of the graph that illustrates this and label it applied matches static friction. So hopefully you agree that this is the, oh shoot.
And why would that happen? Okay, so the screen came back. Sorry guys online, the projector just stopped projecting for a minute. So this is the part that says, and we're going to say, static, oops, sorry. We should say that the other way around, shouldn't we? We should say that static matches the the applied friction. Static matches applied friction. That's what's happening here, right? That's the relationship this is showing. As I increase this by the same amount. That's what a straight line in a 45-degree angle shows, right? So when you see a graph like that, you know what the relationship is. As I increase this, I increase this by the same amount. Okay? This is a linear relationship, and you should be able to sort of say that just right from the get-go. So, now, because the force of static friction matches the applied force, what does this suggest about the type of force the static friction might be? What scenario does it happen in that if I have an applied force, that I have another force that's equal to that? What law is that related to? Which of Newton's law is that related to? If I have a force on something, it pushes back with an equal and opposite force. That's Newton's what law? First law says I resist a change in motion, right? Second law says this is the force it takes to overcome that resistance. The third law says for every force I apply on something, there's an equal and opposite force, right? That's Newton's third law. And that would suggest this is a reaction force. Okay? That would suggest this is a reaction force. But we don't... Oh, crap. We don't actually have this as the case here. Action-reaction forces, how do we know this is actually not the case? Okay, how do we know this is not a reaction force? And if we draw a free body diagram to help this, or to show this, I have a box, or I have an object, right, that's got a force due to gravity, and I've got the box sitting on a surface, so there's an upward normal force, and we know that the normal force equals mg, or equals the acceleration due to gravity, or the force due to gravity, because it's not accelerating up or down, right? Okay, and then I've got an applied force, and I've got a force due to friction that's exactly the same, and we're going to call this Fs for static friction. Okay, I've got an applied force and the force due to friction, and since that object is not moving, those forces have to be balanced. How do I know this is not a reaction force, though? Every time I increase this force, it matches. And that's the hallmark of a reaction force. So why is this not a reaction force? If some of you have peeked at the answer, what might that suggest? What might this free body diagram tell us why that's not the case? Do action-reaction forces act on the same object? They don't. If they did, then nothing would ever go anywhere. Okay? This is the fallacy of the horse. Remember the horse said, if I pull on the cart's going to pull back on me with the same force, and I'm not going to go anywhere. Well, the action and reaction forces aren't acting on one or the other. They're acting on both of them, right? So the object here, the applied force is acting on the object. The friction force is also acting on the object. This cannot be a reaction force because action-reaction forces do not act on one object or act on the same object. Okay, your answer online goes a little bit further into that. Oh, by the way, for you guys online, Caden and Emily, if you want to actually see what I'm seeing, and you may have to do this sometimes, rather than just looking at the presentation that I'm giving over the meet, you may actually have to open up Canvas yourself in a separate tab to see some of the things that I want you to see. You don't need to do that today, but at some points you may need to actually do that. Okay, so the question would be then, if this is not a reaction force, how does the friction force actually match the applied force? It should be astonishing to you that the table can sense how strong I'm pushing on it and push back on me with exactly the same force. Right? It's not accelerating. So however I change that force, if I increase it or decrease it, or if I go back and forth, the table matches that friction force that it's pushing back with on me to the exact same degree. It's not a sentient being, is it? It doesn't sense that force. How does this happen? Okay? So this might tell us something about what really causes friction. You're going to be surprised because it's actually not what you think. Okay? So the answer to this will require us to learn a little more about friction. We'll come back to this question in a few minutes. Okay? A little bit more graph interpretation. According to the graph, what happens to the friction force once static friction is broken? What happens to the force due to friction once I finally break through?
Stays the same.
Well, what's it do first?
It drops.
It drops and then it stays the same, right? And that's what we know. Every time I push on something and I push and push and push and then finally it breaks free, it takes less force for me to keep moving it. That friction force is then going to stay the same, no matter how hard I push. Okay, that friction force is going to decrease and then stay the same. So what I've said is the force due to friction decreases and becomes constant even if the applied force increases. Okay, the force due to friction decreases and becomes constant even if the applied force increases. Okay, two separate situations. I have static friction to begin with, and the friction force increases as I increase the applied force. But once I break that force due to static friction, then I get a situation where the friction force stays constant even if I increase the amount of force that I apply. Okay, so we've got to
we've got to create a hypothesis or come up with some mechanism of friction working in this way. How is it going to work this way? And we want to figure that out. So circle the portion of the graph that illustrates that, and then label it with constant force of kinetic friction. Constant force of kinetic friction and in your handout, I just gave you one graph, didn't I?
Mm-hmm.
Less than static friction. Okay, so this is just an observation. This is what we observe to happen. Okay, and we've modeled this, and we could take that and look at other systems and see if friction behaves in the same way. It behaves in the same way. It behaves in the same way. It behaves in the same way. And we find out that it behaves in the same way enough that we can start to look at this and say, well, what kind of a system is required for this to happen? How does friction work? So maybe the understanding this relationship between applied force and static friction versus kinetic friction can tell us something about what causes the force due to friction. And up to this point in time, your explanation would likely include something about two surfaces rubbing together and that causing one thing to slow down as far as the other one goes, right? So that's not all there is to it. So let's first ask the question, do we ever actually touch anything? Am I touching the board? Am I touching the desk?
Yes and no.
Okay, yes and no. I guess it depends, right? Recall from whatever teaching you've had about matter and atoms that most of the atom is actually space. As the surfaces of solid objects are nothing more than closely packed atoms, and in general, the only interactions atoms have with each other are between electrons. Surfaces don't technically ever touch other surfaces. Okay? Even though we can feel and see contact between surfaces, what we perceive, what our brain perceives to be contact, is actually the interaction of electromagnetic fields of all of the atomic and subatomic particles involved. And we're going to draw a little model of this. Okay? And our initial model is going to look like this. And we're going to say that particles in the surface here interact with particles in the surface here and create little forces of attraction. Right? This is what we sort of see. We have forces of attraction created in here, and this particle is going to move relative to the, or this surface is going to move relative to the other surface. But if we think about this at a more microscopic level, we think that the surfaces are made up of closely packed atoms. And we can say that the atoms are having an effect on each other. And then we can even spread this out a little bit more. And we can sort of put little electron, and they're not really orbits, but electron clouds around. And so at the atomic level, I've got particles and there are little electron clouds. I should draw that a little better, huh? And what happens is that moving particles that are charged create a magnetic field around them. Okay? Now, if I've got electrons that are whirling or waving around the nucleus of the atom, you would agree that these electrons are in motion, right? So charged particles that are in motion carry electrical charge and electrical force, and charged particles that are in motion also create magnetic fields. And so what ends up happening is that the individual atoms that are close enough together create little forces of attraction between them. Okay? And so all atomic or molecular particles exert forces of attraction on surrounding particles. Now, the thing about this is that each of these forces is tiny. Okay, we're talking 10 to the negative 30th or 40th newtons. Okay, that's a lot of, that's not very much force, is it? But if I remember that the number of particles that I have in the surface of a solid object is also in the range of 10 to the 20, 10 to the 30, 10 to the 40th particles, all of a sudden, all of those particles that are in one place exert a fairly significant force on particles on the other surface. When you add up the unimaginable numbers of particles involved in surfaces touching each other, the force of attraction these surfaces has for each other becomes fairly great. And these are the forces of attraction that cause friction. And so all contact forces are stated to be electromagnetic forces. When I push on this is a contact force. I'm pushing on it. That's an electromagnetic force. The electromagnetic fields of the atoms in my hand are interacting with the electromagnetic fields of the atoms in the top of the surface here. And that's what's creating the force. I'm not really touching the object. Now, two factors modify how these forces of electromagnetic attraction occur, how strong they are. How much force pushes the two surfaces together is one thing. The greater the force pushing the surface together, the closer the attracting forces, and the stronger the force due to friction. Okay, so I'm just going to pretend that we don't have very much force acting here, and so the forces of attraction are not very strong here. These little dots are representing the forces of attraction. But if I push these things closer together, these particles in this surface and these particles in this surface are closer together, and those forces become much stronger. Okay? So the less force that I push these together with, the less those forces are. The stronger I push those together with, the stronger those forces are. What might we use to quantify how tightly an object is pressed against a surface? And when thinking about that, consider what would happen to how tightly pressed an object against the surface would be if somebody pushed down or pulled up on an object. What would we probably use to quantify how tightly something is pushed together?
Pounds.
Okay, we're actually going to use newtons because that's okay. But what particular force am I going to use to quantify? If I could say that there's one force in my free body diagram that I'm going to use to say how strong that pushing of the two surfaces together is, what force would I use? Any thoughts?
Applied.
The applied force is actually in the horizontal direction, right? We're talking about in the up and down direction.
Friction force.
In the up and down direction.
Normal force.
The normal force. We're gonna use the normal force. And here's why we're going to do that. The degree to which two surfaces are pushed together is indicated by the normal force. And we're going to draw free body diagrams of a box at rest on a floor with no downward force applied to it. So if I have a box at rest
And we're actually going to say we have an applied force in the horizontal direction. It's not moving though, so it must be a force due to static friction, right? So we've got the force due to static friction opposing it. And then I've got mg, and I've got the normal force. Okay? Now, the normal force is usually going to be equal to the force due to gravity, right? So I could come up here and write the normal force equals the force due to gravity. Okay? But what happens if I start pushing on that box? Okay? Let's say that I push on that box with a new force. I'm going to say force B. Okay, so I'm pushing downward on the box. Does the force due to gravity go away? Does it change? Force due to gravity doesn't change, does it? So now I've got two forces. I've got the force due to gravity and the force that I'm pushing down on the box with, and notice that I made the force due to gravity the same. Now what's happened to the normal force? Does it stay the same as it was here? Does it just equal mg? Is the box accelerating up or down? No, so it has to balance both of those forces now, right? So my normal force now equals FB plus mg. And hopefully you would agree that this surface, the box is pushed more tightly on the surface now than it was before, right? And so the force due to gravity doesn't change. We can't use the force due to gravity in our analysis of this. Okay? We have to use the normal force. So what we're going to say that is that the force of friction is related to the normal force. The greater the normal force, the more friction. And that's intuitive, right? The harder I push down on something, the more difficult it's going to be to change its, or to move it, right? The harder I push down on it, so it's going to be more difficult to move this. And we still had a force of static friction here and an applied force here. Okay? So, why would we use the normal force as a measure of how tightly two surfaces are compressed together instead of the force due to gravity, which is what a lot of people want to use? And so the way that we would explain this is, while force due to gravity on the object does not change, how tightly the object is pressed against the surface can change. A change in the normal force would reflect this. Okay? Change in the normal force would reflect this, whereas the force due to gravity wouldn't, right? The force due to gravity doesn't change. I need a force that's going to be able to change with however tightly those surfaces are compressed, and that's what the normal force does. Okay? So, one thing that affects the force of friction. So if I say the force of friction is proportional to what? And that's what that little symbol means. It means proportional to. We're going to say that the force of friction is proportional to the normal force. The greater the normal force, the greater the force due to friction. And that makes sense because the stronger I push down on something, the more closely those surfaces are compressed together, the stronger those electromagnetic forces are. The second thing that affects this is going to be the roughness of the surfaces at the microscopic level. And it should make sense that the rougher the surfaces are, the more points that the surfaces come close together at, and the greater the number of attracting forces can develop. And so what we're going to show is if I have a smooth surface, relatively smooth surface, I can get that number of forces. But if I have relatively jagged surfaces, it's not so much that these surfaces get in the way of each other. It looks like they're going to bump into each other, but it's going to create greater surface area for these forces. And so I'm going to have more of those forces. Okay? Since there's more surface area now, I can have more of those forces develop. So the rougher surfaces are, the greater the force due to friction. Okay? And we measure the degree of roughness between two surfaces experimentally and create a factor that we multiply the normal force by to determine the force of friction. And we call this the coefficient of friction. And we're going to abbreviate this with the Greek letter mu. Okay, it looks kind of like a U, but if you look at it, it also kind of looks like an M, doesn't it? It's kind of it's the Greek letter M, or mu. You can also call it mu. The correct pronunciation is mu. Okay, so the greater this factor, the rougher the surfaces and the stronger the force due to friction. The thing is, we can't really know enough about the surfaces of materials to be exactly able to predict these. We have to determine them experimentally. Coefficients of friction that represent slippery surfaces are usually less than 0.20. So if I had ice, usually ice is going to be a coefficient of friction less than 1/10. The lower this coefficient of friction, the less friction, right? If I have a normal force of 100 newtons and a coefficient of friction of 0.1, that means my friction force is 10 newtons. And by the way, this is a unitless number. Okay? But if I had a coefficient of friction of 1.1, the force of friction would be 1,100 newtons. Again, this takes a lot of energy too. Sorry about that. Online people, my projector just unswitched again. Come on. Really?
I think your projector still wants to be on break.
Yeah, I think so. Again, online people, the projector just kind of stopped on me again. So I'm trying to reconnect to projector.
Yo. He was, yo. It was like 5 minutes ago. You weren't even. He was like, you still have like 3/4 that left, now you're done. So he just. So he didn't give me that. Yeah.
What class was it?
It's too hard.
Oh.
It was.
That's the one that
And I don't want to stop because we at least need to get this formula written down. Okay. So online people, I'm going to try one last time to get my projector going here.
Yeah. He's in IT. They all know. My brother's in the college.
Okay. There we go. Okay, so just a couple more minutes here then. So what we're going to say is we're going to create a mathematical formula that determines the force due to friction. We're going to say force due to friction equals coefficient of friction, which is mu, times the normal force. Force due to friction times the normal force. Okay, and just real quickly then, we can now talk about why we make the observation that as a force is applied to an object before it starts moving. As the applied force increases, the force due to static friction matches this increase. We need to figure out why this happens. So we've already said that because both the applied force and the static friction force act on the object, they can't be action-reaction pairs. Remember, what we're seeing here is if I've got a box and I've got an applied force, the static friction force increases Okay, now it's not letting me write very well either. Okay, so the applied force increases, the static friction force increases. Why is that happening? Why are these two connected? They're not action-reaction forces because they're acting on the same object. Okay, so, I don't want to, I'm going to scrunch down to this next page here. What I want to draw is a surface and a box sitting on the surface, but I'm going to leave a little bit of space here and put some electromagnetic forces of attraction here. The box is attracting the surface because of the forces of electromagnetic attraction. And I'm going to apply a 50 Newton force to this box. Fa equals 50 newtons. okay? Now, remembering how friction forces develop, what do you think applying the force, this force on the box, does to the surface? And pretend that these are little electromagnetic forces here between the box and the surface are like really tight bungee cords. And if I pull a 50 Newton force on the box, what's that going to do to the surface? If I've got tight little bungee cords, really tight little bungee cords here, like the rubber bands on braces, right? If I pull on that box and there are these tight electromagnetic forces here, what's that going to do to the surface? Isn't it also going to exert a force on the surface? It's going to try and make it move, right? Okay, so with the hold, this isn't going to work. Okay, let's actually stop here because I'm not going to have quite enough time to finish this concept, and then we're going to work on some problems. So I was hoping to get through this whole lesson today and work on some problems. We'll chalk not being able to up due to trying to start online learning or live streaming, and obviously I've got a few things to work out here, but it wasn't terrible. So we'll stop here and we'll pick this up again next time. So if I could get Emily, you, and Kate to unmic or undo your mics, can you talk to me now?
Marshall, what do you want us to do with our Chromebooks at our table? Or
What's that?
do you want us to leave our Chromebooks at our table?
No, put them away. I'm sorry, can you guys hear me? Did I get you talking? Okay, Emily, can you hear me?
And then switch, because I have.
Are you still here?
My counselor's TA.
Caden, was this at least not terrible, just kind of slow and
About only coming these days, anyway.
you thought it was pretty good for the first time?
I'm very happy.
Okay, awesome. I'm glad to hear that. Hopefully we'll just continue to make improvements from here. Okay, and so just go, both of you just go ahead and take pictures of what you got to so far and submit those through Canvas, and we'll just do the rest of it next time. So hang on to those, and but just submit what you've taken so far on Canvas, and that'll give you the participation points. Thanks. Take care. And I'm going to stop the meeting now.
Do you want these?
No, you hang on to yours.
I love